This is just a quick video to clarify some of the units and quantities you're going to need for the Mastering Physics assignment due November 30th. So when we're talking about radioactivity, often they'll give you a mass of the sample in grams. So M would be mass of sample in grams, but that doesn't come into any of the radioactivity equations. What you need is the number of nuclei. Remember, for every atom, there's one nucleus. And so the way you figure out the number of nuclei, n, when we're doing n equals n0 e to the minus lambda t. Remember, this is the formula for radioactivity. This is the number of undecayed nuclei at any given time. So those ones that have not decayed, this is the initial number. And that's usually the number that you have to calculate given the mass. Okay, so to get n, what you do is you take the mass in grams, you divide by the mass number, and that's usually in grams per mole. And then you multiply by Avogadro's number, 6.02 times 10 to the 23rd atoms per mole. And what you're going to come up with is atoms, which is what you need, which is the same as the number of nuclei, because one nucleus. So for example, let's say we had a sample where the mass is 6.13 grams, and then they tell you the mass number, which is also A, which is also the nucleon number, is 124. So whatever that element is, it's got 124 neutrons and protons. And so the number of nuclei in that sample would be 6.13 grams over 124 grams per mole times 6.02 times 10 to the 23rd. Okay, so that's a very handy calculation. Okay, something else. Now, sometimes they'll do this a little differently. If they give you the mass in atomic mass units, so say they give you the mass of the sample in atomic mass units, and maybe you want it in grams, then you can use the conversion that there's 1.66 times 10 to the minus 27 kilograms per atomic mass unit. But usually if they give you the mass number, they'll just give it an integer like this one up here. This 124, that is the mass number. Okay, now another thing you'll come up across is the activity in a couple of different units. Activity, I give the symbol R. Some people give it a capital A, but I don't want to get confused with A, which is the mass number, the number of neutrons and protons. So we'll give it R. The units for this, the SI units are becquerels, after Becquerel, who discovered radioactivity back in about 1887 or so. So becquerel is BQ, and 1 becquerel is 1 decay per second. So it's the rate of decay. So if it's spitting out betas and it has an activity of 1 becquerel, it would spit out 1 beta per second. Now, usually activities are way higher than that. And so that's why we introduced the unit, the Curie, capital CI after Madame Curie. And 1 Curie is equal to 3 now I don't know where this number came from, but it's 3.7 times 10 to the 10 becquerels, or decays per second. So a Curie is a lot of decays per second. Now you often have microcuries, millicuries, like 1 Curie is a pretty huge activity for a radioactive sample. Okay, so some other handy things that you're going to need. Remember, I did this on the formula sheet. We'll do it again here. The activity is equal to the initial activity e to the minus lambda t. The activity is also equal to lambda n at any given time. And so R0 is lambda n0. And remember, lambda is the decay constant. And usually they want that in seconds to the -1, but it could be in days to the -1 or years to the -1. And that decay constant is then related to the half-life. So the decay constant is ln 2 over T1/2, where this is the half-life. That's the time it takes for 50% of the nuclei to decay. Okay, so that's how those things are related to each other. And don't forget also, of course, that n is n0 e to the minus lambda t. So also the activity is the time rate of change of the nuclei, decays per second, right? So R is in decays per second, or becquerels, decays per second. But usually they'll give it to you in curies, in which case you have to convert to decays per second before you use it. Okay, one more thing that you're going to come across in that assignment for Monday is when you're doing fission. Fission is when, this is what they use in nuclear power plants to generate the energy. So it's when a big parent nucleus breaks into two smaller ones, say Y plus Z plus, usually neutrons come out, multiple numbers of neutrons come out, however many, 3 or something, doesn't matter, whatever. Neutrons don't have any charge. When you're doing the calculation for this, the energetic situation, you take the mass of this. Now it is only nuclei, but you don't have to worry about the electrons because the electrons all balance. So however many, remember, we're not spitting out any electrons. So you can just literally take the mass of the whole atom, of the whole X, and then subtract the mass of the Y, subtract the mass of the Z, subtract the mass of those three, will have to be 3 times the mass of the neutron. If that number is greater than 0, this thing will go spontaneously. Now, often that it doesn't happen, it doesn't work. That's why you need an extra neutron to kind of, it's like the straw that breaks the camel's back. You need to add to the X. So you bombard it with these slow neutrons, and that's just enough to get it to break apart. And then you get multiple neutrons coming out to get it to go. Okay, so that's all you probably need for now.